So here I have a couple jars. This is slightly cold water, and I'm going to put in the other jar hot water. And I'm going to keep the volume the same for the most part. I mean, as close as I can. So the volume should be essentially equal. And I'm going to put 1 drop of food coloring in each, and they should be essentially equal. But we'll see different things. Okay. So if I put 1 drop in the cold water, now I've made my solution, and you can see it's starting to travel down and spread out. But if I put 1 drop in the hot water, it's much faster. Why is that? Any ideas? Anybody know why the hot water would cause the dye to spread out more?
The molecules move faster and hot.
Yeah, right. So we have thermal energy in the hot water that's higher than the thermal energy in the cold water. And as we know, when you put heat into something, you essentially increase the entropy. And so what's happening? In the hot water, yes, the molecules are moving around more because there's thermal energy. And as we see, we have more microstates. It's become disordered more quickly. This has lower entropy because it is still somewhat ordered. Ordered meaning that the dye is more collected together. This is higher disorder. And so this shows the relationship between heat and disorder, heat and entropy, using a solution. Now, what's happened? This has basically reached equilibrium, the hot water. The cold water has not reached equilibrium yet. So temperature affects the rate at which something reaches equilibrium. And eventually, maybe halfway through the lecture, maybe at the end of the lecture, these two will look the same. But for now, they don't. Okay? And so let's get into equilibrium and see why that is the case. Let me share my screen. Let me get to the slide deck. Okay. I am recording, and let's do this. Okay. So if you guys were on campus, you'd be familiar with the chemistry lab, and you'd know that there's this sticker on one of the cabinets that says, "Old chemists never die, they just reach equilibrium," which is a really nerdy joke that that chemists like to say. So unfortunately, we can't be on campus yet, and so you won't see this sticker. But I wanted to show you that so that you got a little bit of feel for the lab itself, other than the virtual on-campus labs that we've been doing. Also, I wanted you guys to know that the midterms are graded. So I should have posted basically all of your scores. I need to scan your exams, and then I'll send those to you as well. Here's a little joke, another joke. Me during thermodynamics exam, after Q equals MC delta T doesn't work, you just throw whatever at it. And I encourage that, right? Like I've said before, if you don't give me anything to grade, I will have no points that I can give you, right? If you leave something blank, I don't have much to work with. But if you're working through these problems and something isn't working for you, just try your best. Now, don't make it so random that I can tell that you're just writing stuff down, but again, do your best. And with these exams, with the midterms, I was really happy with how they went. You guys all, for the most part, did very, very well, which I guess means that it was too easy. And then I'm going to have to make the final a lot harder, right?
No, it just means that you're an amazing teacher and we understood everything because you taught us so well.
Now, I like that outlook. I think that was Hannah. Thank you. Okay, well, maybe I'll go with that interpretation then. We'll see. But anyway, you guys did really well. And so if you guys do want to discuss the midterm at some point, you can see me tomorrow during office hours, and we can, go over some of the problems if you had some sticky spots. Okay. All right. So that brings us to equilibrium. Now, what we've learned last week is that reactions can be spontaneous, meaning they go toward a natural progression, or non-spontaneous, meaning they need to have some kind of outside input to make them go a certain direction. And we also talked about whether or not reactions are reversible. We said that phase change is reversible, right? If you want something to go from a solid to a liquid, you add heat. If you want it to go back to a solid, you remove the heat in the same step, in the same increment, in the same amount as you put in. They're reversible if they can be changed without extra energy. Okay. Now, what that brings to today is when that forward and backward interchange between the reactions happens at the same rate, then we reach equilibrium. Okay. So when the products are going back to reactants and the reactants are driving forward into products at the same rate, both of those things are doing it at the same rate, we reach equilibrium. Okay, it doesn't mean that the reactants concentration is equal to the product's concentration necessarily. It just means that it's going back and forth at the same rate. Okay. And when that happens, it's reversible, and entropy is going to be equal to 0. There's no change. There's no further energy required to make that system go one way or the other. Now, what we'll learn is that you can add in energy. If you change the temperature, you change the equilibrium. Also, if you change the pressure, if you change the volume, all of these things will change the equilibrium or disrupt the equilibrium. And then it will, over time, balance itself and get back to a state of equal rates. Okay. I did want to point out, a couple of you mentioned this to me in my last recording. I forgot to do a subtraction on that last part. So when we were calculating delta G, we calculated it for basically water vaporizing at room temperature right here. And then we said, well, what about the vaporization of water at 125 degrees? And when I calculated the free energy for room temperature, it was positive, which it should be, because if we look back at our little chart here, come on, right? When delta G is greater than 0, it's non-spontaneous. So water evaporating at room temperature, like boiling essentially, right? Not evaporating, but just for it vaporizing at room temperature is not a logical thing, right? Water doesn't boil at room temperature unless you put in some kind of energy, you decrease, you increase the pressure and stuff like that, okay? So that's good. But when I did my calculation for G for 125, I got a positive number for that too. And that's because I forgot to subtract two things in that equation. And if you subtract those two things, you end up getting a negative answer, which is the right answer, because a negative G less than 0 is spontaneous, right? And water boiling at 125 degrees Celsius, that happens, right? It doesn't need any outside intervention to make that happen. So that would be spontaneous. Okay. So if any of you else were watching that video and like, I don't know why that doesn't make sense. It shouldn't make sense because it was wrong. All right. So getting back to equilibrium. As I said, we can perturb equilibrium in several ways: by changing the concentration of the reactants and or the products, by changing the temperature of the system, right? I don't know if you can see, this is almost the same as this. I still see some swirls on my end. I'm not sure if it's coming through to you guys, but the temperature is changing the rate at which these reach equilibrium, or the pressure. Those three things affect equilibrium. Now, all reactions can be considered reversible. However, usually they will either proceed in one direction or the other. Most commonly, the reactions are going to proceed until reactants are exhausted and you are left with your product, right? And we know about that when we learned about stoichiometry last semester, limiting reagent, right? Once the limiting reagent is used up, it can no longer proceed and get more product. Okay, that's how typically things work. But equilibrium is dynamic. Okay, what does that mean? That means when a system has reached equilibrium, it doesn't mean that things are static, that the reactants are now what they are and the products are now what they are. It's going back and forth. Okay, the reactants are continuing to turn into products, and the products are continuing to go back into the reactants. What makes it reach equilibrium is that they're doing it at the same rate. Okay, so the products are going back to reactants at the same rate that the reactants are driving forward into products. And we'll talk about rate kinetics and stuff next quarter, because again, all of this just piggybacks on the stuff we've learned previously. But I liken it to these jugglers here. Okay, we can think of, let's say the juggler on the left is, let's say this represents the reactants, and the juggler on the right represents the products. If it was static, they would just have their pins and they wouldn't be going back and forth. Okay, and we say, oh, it's at equilibrium because it's stopped. But that's not what equilibrium is. The reactants are continuing to lobby those pins over to the products. And the products are continuing to lobby the pins over to the reactants. But the difference is that they're doing it at the same rate. So nothing overall changes. Okay? That's a good analogy for equilibrium. It's not static. It's not that things have just held still. There's back and forth, but at the same rate. Okay, I know it's a broken record, but I'm just trying to burn that in. Okay, let's erase that stuff.
Hey Carl, did we say that saturation is equilibrium too?
Saturation. So saturation involves solutions, right? And you can drive a saturation one way or another based if you change the temperature, right? But I think your question is, when it has saturated Is it at equilibrium?
Yeah, basically like, salt water when it can't hold any more salt anymore. Is that equilibrium or not? I'm wondering.
You could think of that as equilibrium. So before we get to supersaturation, right, when we've added every single salt crystal to the water that we can, then yes, it's not going to go further. So, but again, equilibrium in that context would be the sodium chloride deionizing, binding with water, and then coming back to form sodium chloride again.
And is that not represented as an equation, just like a chemical equation?
It is. So, right? So if we have that going on, you would have NaCl. Can you guys see this? Let me stop sharing real quick. NaCl going back and forward. Plus let's add the water. Going to Na plus Cl minus H2O. So at some point, it's going to be going to this, right? But even at equilibrium, what we're saying is it can go back this direction.
And it's happening continuously in that case, or no?
It's happening continuously, and when it's at the same rate, it's equilibrium. It doesn't mean necessarily that this goes to this and then it can't go to that anymore, right? For saturation, it just means that going back and forth, back and forth, back and forth at the same rate so that overall nothing changes.
Okay.
Now, if you reach saturation, you continue to add things. That doesn't mean you go beyond equilibrium. It could still be at equilibrium.
Yeah, and like the stuff that's maybe out of solution, precipitate at the bottom is continuously becoming solution, but then more is being precipitated out at the same time.
Yes. So the stuff you add that doesn't dissolve, in theory, you could say that those do dissolve, but as they dissolve, other sodium and chlorine ions come out of solution.
Okay, cool.
It's a good question.
Thank you.
I always like your outside the box questions. They challenge me. Sometimes more than I would like, but it gets me outside of my comfort zone, and that's a good thing. So thanks. Okay, so that's the analogy, that it's a dynamic process. Phase change can also reach equilibrium. So if we had bromine and it was in this closed vial, okay, and we kept the temperature constant and the pressure constant, and we of course couldn't add anything in there, and we couldn't have anything leave, eventually it's going to reach an equilibrium where it's going to be going from liquid to gas and gas to liquid, but at the same rate, so that things don't change in that system. So we can think of equilibrium in the context of reactions, but we can also say that phase change can be written as a reaction as well. So it's also translatable to phase changes. Eventually, you'll reach a homeostasis, okay, where you don't get any more gas, you don't get any more liquid, they're going back and forth, but at the same rate, so it essentially neutralizes itself. Now, yesterday and today for lab, you guys got a little bit more familiar with this concept of a reaction quotient. And if you didn't make the labs, then you're going to learn it right now. But the nice thing about having material in a lab before we actually go over it in lecture, as I've said, is that when we go over it in lecture, it's already been put into your brain a little bit to percolate. So hopefully this is just going to be a nice little review for you guys, right? What is a reaction quotient? We designate that as Q. And we say that the reaction quotient is the ratio of the molar concentrations or pressure, as you guys learned in problem 4 of the ICA. It's the ratio of those concentrations or pressures respective to products and reactants, okay? Raised to the power of their coefficient. So we have a generic formula here. Let me move this out of the way. We have a generic reaction. A plus B yields C plus D. So A and B are the reactants, C and D are the products. And then it has these coefficients or their molar concentrations, right? M is going to be the coefficient for A, and N for B, and X for C, and Y for D. If we wanted to write that out in an expression, an equilibrium expression that reflects the ratio of those things to each other, then that's how we get what's called the reaction quotient. So we're going to say Q, in this case, QC, meaning it's concentration that we're taking into account. If it was P, then it would be pressure. QC is equal to, again, remember, like usual, products over reactants. So C raised to the power of its coefficient, X, times the concentration of D raised to its coefficient, Y, all over the reactants, A to M, B to the N, okay? And the brackets, again, those brackets are used to depict that they're concentrations. So this is the generic form that we use to write equilibrium expressions. And come on, next slide. There we go. So let's try it, okay? You guys have already had some practice. So what I want you to do is I want you to work on A, B, and C, and then we'll go over them, okay? Remember, products over reactants. I'll give you a brief period to do that. Take my coffee break. I'm back to drinking coffee. My stomach has resolved all of the issues from last week, and so this is the final test when I could start drinking coffee again. I knew that my tummy troubles were behind me. So cheers.
So, Carl, is it the molar weight we're plugging in for each of those elements?
No. So this
What
is
again?
just
Sorry.
this is just generic at this point. Okay.
Oh, okay.
Just write in the reactants and the products in these reactions. Don't worry about the actual numerical values.
Gotcha.
So A, for instance, is going to be, what are they asking for? The expression. So we'll write Q equals O3 raised to the power of 2 over O2 concentration raised to the power of 3. All right, what do we get for B, guys?
NH3 to the 2 over N2 H2 raised to the 3. N2 doesn't have a power. The 3 goes for the H2.
Okay. Great. Last one, C. What do we get for C? I stopped sharing my screen, so I can't see what it is. You gotta help me. Nobody get to see yet?
I got the top part, but then you stopped sharing before I could finish the bottom.
Oh, well, so there is the slide deck on Canvas. If you guys want to open that up, you can follow along that way too. I always post my slides ahead of time, but maybe I sabotaged you with this one. So we'll go back and share the screen. Okay. So it's just products over reactants, right? NO2 to the power of what?
4.
4 plus H2O to the power of 6. And then ammonia to the power of 4. And oxygen to the power of 7. Okay? This is as simple as it gets. So if you guys have this firmly, you're good. We're going to be doing this throughout the entire chapter, right? We got to do this to then get to the answers later on for equilibrium. Okay. Now, K. Let's introduce K. What is K? When the value of the reaction quotient is at equilibrium, okay, meaning when the products are going to reactants at the same rate that the reactants are going to products, we then say that it's K. That is the constant for that particular reaction. Different reactions are going to have different Ks, right? They're going to have different constants. What is the K? It's just the ratio of those two concentrations of reactants and products, right? So depending on the reaction, its ratio is going to be different to reach equilibrium than some other reaction. And again, reactions go back and forth. When you breathe in the oxygen, right? And it binds to hemoglobin. That could be a reaction. Oxygen plus hemoglobin yields hemoglobin and oxygen bound together. And then what does that do? That has an equilibrium constant to it. Then the blood takes that hemoglobin and oxygen bound together and delivers it to parts of your body that is low in oxygen. And then what happens? The reaction reverses. The hemoglobin and oxygen break apart into separate entities again, right? And luckily that's the case, right? If hemoglobin and oxygen had a high affinity for each other, then it would just go through your blood and they would stay together and they just process throughout your entire system. And you'd never deliver the oxygen to your deoxygenated body parts. But luckily, the way it works is that when hemoglobin and oxygen are in a highly oxygen concentrated environment like your lungs, they bind. And then when you deliver them to places that has very low oxygen, like your muscles, they separate. Okay. At equilibrium, K and Q are equal to each other. All right. That's going to be at a given temperature, right? Because remember, temperature can disrupt equilibrium. So the reaction is at equilibrium at a given temperature. And the Q is going to have the same value because the K is also that same ratio of products over reactants. So let's try this, okay? Gaseous nitrogen dioxide forms dinitrogen tetroxide. And this is a common reaction that we use in equilibria because it goes back and forth quite readily. And what we're saying is when we have 0.10 moles of nitrogen dioxide and we add it to 1 liter flask at room temperature, the concentration changes so that at equilibrium, now nitrogen dioxide is at 0.016 molar. And dinitrogen tetroxide is at 0.042 molar. So what's that saying? They gave us 0.10 moles per 1 liter. So the molarity is going to be still 0.10 because 1.10 divided by 1 is 0.10. Okay, so we're saying that when we add that amount for it to reach equilibrium, it shifts and the concentration changes. It reduces itself. It goes from 0.1 to 0.016. And then we get a product, dinitrogen tetroxide. What is the value of the reaction quotient before any reaction occurs? So reaction quotient is Q. So see if you guys can set that up. You would put product over reactant. And then what is the value for the equilibrium constant? K for the reaction. The first one I think might be a little misleading. So I'm going to go over that one and then I'll let you guys do the second one. So for A, it's saying, what is the value before any reaction occurs? Okay, so we're going to say QC is equal to products. That's going to be the concentration of dinitrogen tetroxide over nitrogen dioxide, and the coefficient there is 2. So what is this? What is this concentration on top? This is the tricky part, maybe. What do we put it? Well, what do we put here? Let's do that. Point 0 or 0.10, right? Because they said 0.10 moles in 1 liter. So we said the molarity is 0.10. What's the concentration of dinitrogen tetroxide? Anyone? It says
0.042.
no. That's the tricky part, but thank you for volunteering. It says before any reaction occurs.
Do we just need to find the molar mass of that?
No,
H2O4?
you're overthinking it. If no reaction has occurred yet, there is none of this.
So
Huh?
just 0?
It's 0. Okay, so that's why it was tricky. No reaction is formed, so there is going to be none of the dinitrogen tetroxide. So it's 0 divided by 0.1, that's 0. So Q equals 0. Now, the second part, this is the part where I'm going to let you do yourself. Okay. It says, come on, what is the value of the equilibrium constant? So now we're wanting to solve for K. They give us the concentrations at equilibrium. So what would we do there?
0.042 over 0.016.
And then any coefficients there?
Yeah, the bottom is raised to the 2.
Okay. So to calculate K, you just take 0.042 divided by 0.016 squared. And what do we get for that?
$164.06.
Okay. That's high, right? That would be a large K. And we'll get into what that means when the value of K is high versus if the value of K is low. Spoiler alert, if the value of K is high, then it's going to highly favor the products. Okay. Any questions so far? Are the KC given values? Sometimes, yes. I mean, we basically have equilibrium constants for most of these reactions, but problems that you will receive in this class will be a mixture. Some will say, this is the KC, so find the respective concentrations at equilibrium. Or it might be like this problem. Here are these, find the KC. And then if you wanted to validate that, you could probably look it up somewhere and see, oh, well, is that the equilibrium constant for this reaction? And if so, bingo, you're good.
KC doesn't have units, correct?
No, I mean, you could, that was a question asked during the lab. You could have units, but since this is a value that is translatable between concentration and pressure, units can be disregarded. Okay, it's really just a relationship of the products and reactants. And so don't worry about units for K. Good question. Okay, let's try the next one. The Haber process, created by Fritz Haber and Carl Bosch in the early 1900s. They won the Nobel Prize for this. It basically is a way to create artificial fertilizer, or also explosives, which was the major intent. So during the World Wars, when a nitrogen ban was put on Germany, they were having problems coming up with enough nitrogen to create bombs. And so creating artificial nitrogen by using this Haber process allowed them to get around that. And just global use of fertilizer to feed an ever increasing population was requiring more and more nitrogen as a fertilizer, right? And they would get that from bat guano and stuff, but they were running out of those stores. And so this really revolutionized the rate at which we could produce crops and, unfortunately, weapons. But anyway, it's a very simple reaction, right? Nitrogen gas and hydrogen gas forms ammonia. And if we say that the reaction of the equilibrium concentrations are the following, calculate the equilibrium constant. So You guys do that, just plug and chug. Of course, you got to know your equilibrium expression, but we know that because we've done it several times now, products over reactants. And see what you come up with for your K. Okay, so hopefully you got something like this. The concentration of the product over the concentration of the reactants raised to their respective coefficients. And if you plug that all in, what does that get us? 0.72 squared divided by 0.1 times 0.2 cubed.
648.
Okay. Everybody else got that? Anybody get a different? Okay, see a thumbs up. Good. So again, another situation where the K is large. So that's going to be a product favored reaction, meaning at equilibrium, you're going to end up with a system that has more ammonia than individual hydrogen and nitrogen. It doesn't mean that what becomes ammonia stays ammonia and what hasn't become ammonia stays hydrogen and nitrogen. It just means that at equilibrium, when they're going back and forth at the same rate, you're going to have more ammonia. Okay.
Does that mean in the ice table that would be the positive side? The ammonia would be?
Say it again. I missed that.
Does that mean like in an ice table, like what we were doing in the ICA, that the ammonia would be the positive side?
The ammonia would be the positive side. In that case, if Q or if K is large, yeah, I see what you're saying for the change, right? Getting back to the change.
Yeah, just trying to figure out which side was positive and negative. I just didn't entirely understand that in the ICA before.
Right. And we'll get into, so I don't know if we'll have a chance to do ICA problem, or I mean, sorry, not ICA, ice tables today, but let's talk about in a few slides, we'll get to the relationship between K and Q, and then see if that makes more sense when we get to that point. Is that fair?
Sounds good.
Okay, great. Thanks. Here we are. Okay. So again, K is significantly larger than 1. It's product favored at equilibrium. If K is significantly less than 1, it's reactant favored at equilibrium. So again, using this juggling analogy, if K, right now, the pins are balanced, right? Each juggler has 2 pins in their hand, and then there are 4 pins in the air. 2 are on one side, 2 are on the other side. So, we could say that that's equal. We have equal product, equal reactant. But if K was significantly larger than 1, then we could say that in that case, there would be more of these pins over on this side. It would be, because remember, this is product, this is reactant. We would say that there'd be more pins on that side. And then so that product juggler would be juggling more pins and then throwing one over, at the same time, the reactant is only juggling maybe 2 pins and throwing one over to the product. Each time the product throws a pin to the reactant throws a pin to the product. The only difference is that the reactant is juggling less pins than the product juggler. Now, if the K was really small, it'd be the opposite, right? The reactant juggler would be juggling all the pins and sending one over and then getting one. As soon as it sends one over, it gets one back at equilibrium. So if K, now how does this relate to the reaction quotient? If K is larger than Q, the reactant will proceed forward or to the right or to the product side, okay? Remember, Q is just the relationship of the ratio of the products and reactants, whereas K is that same ratio, but whatever those concentrations or pressures have to be for it to reach equilibrium. So the values could be different. If we give you a Q that's not at equilibrium and it's less than K, then it's going to go toward products. If Q is a lot smaller than the ratio, if K is a lot smaller than the ratio, then the reaction is going to proceed backward toward reactants. Okay. If Q and K are equal, then it's at equilibrium. Okay. If those values are the same. So we'll have problems, and Alia will get to those problems where you have to determine, based on the relationship of K and Q, whether or not the change is positive or negative. We'll have problems where you have to look at these relationships to determine which direction is going to be favored. Okay, it might be a problem where it says, this is the K, or no, this is the Q. Figure out what the equilibrium concentrations are, solve K, and then determine which is going to be more favored, right? So you have your Q already, you do your ice table, you find your equilibrium concentrations at the bottom, and then you solve for K. And if K is greater than Q, you say, well, there's going to be more product at equilibrium. If K is less than Q, you're going to say, well, there's more reactant at equilibrium. It doesn't mean you can't drive it to more product. And, when we talk about manufacturing in an industry setting, the goal is to get product, right? You're producing something, whether it's fertilizer or some kind of pharmaceutical drug, right? Or some kind of solvent, some kind of, I don't know, whatever, cleanser, right? You want to drive reactants into products because the product is what you are monetizing. And if you are making money off of a reaction that favors reactants, meaning once it reaches equilibrium, just a little bit of it becomes the product, that's not efficient. And so you can do things to change that. You can change the equilibrium by doing what? You guys remember?
Changing temperature, pressure, or volume?
Concentration, isn't it?
Yes. Good. Temperature, concentration, pressure. Those things change the equilibrium. So if you were using a reaction that at equilibrium yielded very little product, you could change that and drive it to more product by changing the temperature or changing the pressure or changing the concentration. All right. And there's an example toward the end where there's an apparatus that lets, for the Haber process, right? There's an apparatus that lets out certain gases so that the concentration changes and drives it more toward the product side. Okay, so just tweaking around things to get K greater than Q. Now, equilibrium can be reached from either direction. And I want to make sure and give you guys a break. So maybe let's take a break now. Let's take a 10-minute break. Let's take a 9-minute break because it's 2:01. And I know that Matt likes to be on nice, even numbers. So let's come back at 2:10 and we'll get into this next part. Okay. So get a stretch, get a drink or a snack, go to the bathroom, and I'll see you at 2:10. Okay, guys, it's 2:10. I just wanted to redirect your attention back to our little demo at the beginning. Now it has been at least an hour, and I hope you can appreciate that this is the hot water, this is the cold water, and let me get out of the way of that. There is still dye that hasn't completely disordered itself in solution. And it's much more visible on my end. So if you don't believe me, try it out. Chances are you probably have food coloring at your house. And just do hot water and cold water. And you can kind of hopefully see, like right here, it's darker. And going down here, it's a little bit darker here than say right here, that's lighter blue. That's because it hasn't completely disordered itself and gone into solution. Okay, it hasn't reached equilibrium yet, you could say. This one has, and it did almost instantly because temperature matters. Okay, now let's get back to things. Back to my screen. Any questions on this stuff before we continue? Okay. So, equilibrium, again, is just the point at which the reactants are going to products and products are going to reactants at the same rate. So it can be achieved from either the product side or the reactant side. Let's say we have 4 different experiments here in this table above. And we have, oh, that should look familiar, dinitrogen tetroxide and nitrogen dioxide, right? What this is showing is that in experiment 1, we start with no dinitrogen tetroxide and a certain concentration of 0.02 for nitrogen dioxide, okay? And in experiment 2, same thing, 0. For experiment 3, 0. And then we have different concentrations of nitrogen dioxide. But in the 4th experiment, we do something different. Instead of starting off with nitrogen dioxide, we start off with dinitrogen tetroxide. And if we plot the concentration of nitrogen dioxide over time to see at what point it reaches equilibrium, they're going to come together, whether we're starting with that material, like in experiment 3, we're starting with nitrogen dioxide at 0.04. So right here, okay? That's the concentration. And we're going to see over time, at what point does this go down and start to plateau or level off? Because once it levels off, that's equilibrium. If we start with it, we get to a certain point where it levels off at around 0.2. Okay. I'm sorry, 0.03. 0.03. If we start, however, with dinitrogen tetroxide, then there's going to be, in experiment 4, there's 0 nitrogen dioxide. Okay, so we're starting with 0, and it's going to increase over time. And the point at which that levels off is going to be at the same spot. Okay, so again, equilibrium remains the same, whether or not we're starting with reactants and going to products, or we start with product and go to reactant, because that is the value at which those things are at the same rate. And so this is just showing that in a graph. Okay, whoops. So again, to drive it home, at equilibrium, the forward and reverse reactions proceed at the same rate. Okay, so dinitrogen tetroxide turning into nitrogen dioxide is going to lower its concentration, right? Now, if we plot, instead of the concentration over time, if we plot the rate over time, the rate at which dinitrogen tetroxide is decreasing and the rate at which nitrogen dioxide is increasing, when they meet and come together, that's the equilibrium. And remember, the rate is the same. So these two lines should intersect. Okay? Because they've reached an equal rate. This is a graphical way of representing equilibrium. Maybe doing a better job than me trying to explain it with words. Okay. Now, if we plot concentration, that's going to look a little different, right? They're not going to meet at the same, because remember, equilibrium doesn't mean equal concentrations of reactants and products. It means equal rate. But at that equal rate, the concentration doesn't change. So in this case, what this diagram is showing is concentration over time. It's showing that in this reaction, when it reaches equilibrium, we have a higher concentration of what? Which one of these has a higher concentration?
Nitrogen dioxide.
Yeah, NO2, right? So it's going up here, it's increasing, and then it levels off. Dinitrogen tetroxide, it goes down. Its concentration is going down, but at some point it levels off. And when those two level off, that is going to be equilibrium. They're not touching, because at equilibrium, for this reaction, it's going to favor nitrogen dioxide. Okay. Now, if we're dealing with solids and liquids and the production of gas, as long as we have some of those products and reactants, gas remains constant in a closed system. So let's say we have this reaction here, calcium carbonate forms carbon dioxide and calcium oxide. And it's in a closed system. Okay, so it's in this jar. And what we're showing here is that if you look, this little powder here, there's more calcium oxide than calcium carbonate. But when we go over here, now it's switched. Now we're favoring calcium carbonate over calcium oxide. There's more of it. But the interesting thing is that as long as this is closed and the temperature is constant and the pressure is constant, the amount of CO2 gas up here remains the same. Okay. Now, if one exhausted, if one of these molecules was exhausted and there was no more of it, then things would start to change, right? It wouldn't be at equilibrium. This is demonstrating in another way equilibrium. The amount of gas doesn't change. It remains constant, but the other reagents are changing in their amounts. Okay. So kind of cool, right? This is what's going on. This is what equilibrium is. Okay? And these are the ramifications of equilibrium. So if you were trying to produce carbon dioxide, it wouldn't matter how much of the calcium oxide and calcium carbonate you had, as long as you still had it. If you wanted to reduce carbon dioxide, then you would have to you'd have to reduce the, which one? Whoa, which one would you have to reduce? Would you have to reduce, do you think, would you have to reduce calcium oxide or calcium carbonate to start reducing carbon dioxide? Well, carbon dioxide cannot go away if there's no calcium oxide for it to react with, okay? So you'd have to start getting rid of calcium carbonate completely. If you get rid of the calcium carbonate, then the carbon dioxide and the calcium oxide will start reacquainting them with each other, forming calcium carbonate. Okay, so in this similar vein of doing multiple experiments, here's a problem where we're starting off with certain concentrations of reactants and products. And we have 3 different experiments for this carbon monoxide plus water yielding carbon dioxide and hydrogen. That's the reaction. The Kc, or the equilibrium constant, is 0.64. And now they want you to determine the direction in which the reaction proceeds as it goes to equilibrium in each of the 3 experiments. So remember what I said. If K is greater than Q, it's going to be what favored? You guys remember?
Reaction.
Product. If K is greater than Q, it's going to be product. If K is less than Q, reactant. So what you want to do here is you want to take these values and put them in an equilibrium expression and solve for Q, and then see if it's greater or less than K. And then that will tell you whether it's forward or reverse. So work on that, and then we'll come together and we'll go over it, okay? No. Okay, so for this first Q, as it turns out, it's basically 0.0040 squared divided by 0.0203 squared. And that's going to give you some number. Did anybody calculate that already?
0.0388.
Okay. 0.0388. And what did we say the Kc is? Kc, or the equilibrium constant, is 0.64. So in this case, so in this case, K is greater than Q, right? And so that means it's not at equilibrium yet. And so which way is it going to go? What's going to be favored?
Products.
Product. Okay. So it's going to go to the right. It's going to go that way. And it's going to favor the products until this number equals this number. And then they're at equilibrium. So then just do that for the next two and see if it changes as the experiments. This is experiment 1. I'll pull that back up for you. Whenever you guys are ready, just kind of shout out what you got. Experiment 2. What do we get for the second one, guys? When you plug in those values for our equilibrium expression.
14.1.
Oh, I'm sorry.
14.1.
Okay. So now Q is much greater than K. So now which way does it go?
I got 140.1, but I may have just entered that in wrong. It seems a little high.
140.1. Okay. So someone has a decimal point off. Let's do a tiebreaker. 14.1 or 140.1?
140.
140. Okay. Well, 140 as is. Either way. Oh, no, I got a 14. Remember, it's one is 0, 0, 0.00. The other one is 0.0. I suspect that's where the problem is. Oh, I got another.
In that case, it's 140.
14. I got, it's a toss up here, guys. I'm seeing some comments come in. 14. Should I be the tiebreaker? Make me do it here. Okay. Let's see. 0.037 times 0.046. I got 140. I got 140.6 though. Either way.
Yeah, that's what I got
I
too.
got 140.6 as well.
140.6. Okay. All right. So either way, the point, no pun intended, the point is that Q is high. much higher than 0.64. And so it's going to be much greater than K. And so it's going to go the reverse way to get to equilibrium, and it's going to favor the reactants. Okay. Whether it's 14 or an order of magnitude greater. Now, the last one. What do we have for that? We have experiment 3. Let me erase my concentrations. Point 0015, 0.0015, 0.0076, 0.0094, and 0.0025. Anybody get to number 3?
I got 0.485.
485. Okay. So in this case, again, Q is less than K, right? 0.485 is less than 0.64. And so it's going to go this way and favor products. So all this is to say that you can change the direction of the reaction by changing the concentrations. In those experiments, all we did was we tweaked the concentrations of these things and drove it toward one side or the other. And that's what chemists do in the real world to achieve a certain product. Okay. All right, now I'm going to ask more of you guys. I'm going to ask you to write the formula as well. So we have nitrogen reacting with chlorine to form nitrogen trichloride. That's the reaction. That's the formula you have to write and balance. And then it says at equilibrium, the concentrations of each gas were 0.15 for nitrogen, 0.25 for chlorine, and 0.5 for nitrogen trichloride. Write the balanced formula and then calculate the K. So you just write the formula. The formula helps you figure out the equilibrium expression. Plug in those things and see what K is. And I might add a little, well, no, we don't. No, never mind. Just we'll stay there for now. I'm blocking it. I wrote it up there. Did anybody get the balanced equation so far?
Yes.
Okay. What'd you get?
N2 plus 3Cl2 yields 2 NCl3.
Perfect. That's what I got too. Now you have your coefficients, and you use those and the concentrations to write your equilibrium expression. Which I did right here. Products over reactants. Coefficient of 2, so product is raised to the second power. 1 and 3, so 0.15 to the first power and 0.25 to the third power. Anybody get an answer?
106.7.
All right. Great. That's it. Let's do another one here. Carbon monoxide reacts with oxygen to produce carbon dioxide. Equilibrium concentrations for oxygen and carbon dioxide are 0.1 and 0.75. If the Kc is 4,000, what is the concentration of CO at equilibrium? So again, just the same thing, guys, only instead of solving for Kc, we give you the Kc and we ask you to solve for the missing variable, right? So set this one up, do it, and then we'll go over it, okay? Okay. Okay. We ready to proceed? I don't want to rush you guys, but I also want to make sure we cover everything that we want to cover today, or that we should cover today. I did it backwards. I did the expression incompletely, and then I wrote the balanced equation. But what do we get for the formula? Anyone?
Two CO plus O2 yields 2 CO2.
Hey, that's what I got too. Great. Off to a good start. So we are given concentrations of our CO2 and of our O2, and they want us to find our CO. And they give us our Kc. And now we have our balanced formula. We can put our coefficients as a expression of an exponent. And see, it's x there, okay? So now it's 0.75 squared divided by 0.1 times x squared, right? So we could write that out as 4,000 equals 0.75 squared divided by 0.10 times x squared.
Daddy, can I use this tiny dry erase board?
And then from here on out, it's just algebra, right? So we can multiply both sides by 0.1 times x squared. We get 0.10 times x squared times 4,000 equals 0.75 squared. Actually, I'm not running out of room here. And then essentially, I'm going to hop back up to the top. So I'm going to erase this, guys. So then to get x by itself, we have x squared equals 0.75 squared times, divided by 0.10 and 4,000. Or 400, I guess, if you want to crunch them together. And what do we get for that?
X squared equals 0.001406.
Okay. And then the square root of that?
0.03.
So the answer is that at equilibrium, when we have carbon dioxide at 0.75 and oxygen at 0.1 molar, our carbon monoxide is going to be 0.03. So it'll look like this: 0.03, 0.10, and 0.75. Okay. Come on. There we go. Any questions on that, guys?
Can I just see the concentrations behind you one more time?
Sorry. Yes.
Thank you.
Oh. Clyde, my aged golden retriever, he's going to be 13 this year. He just got up and left. I think he's had enough chemistry for one day. And luckily we only have 6 minutes left. So he has just a good internal clock. He knows that it's time to finish up and then go for our walk. Maybe this is a good point to stop. Let's see. Can I?
Yeah, it is.
Oh, okay. Bennett seconds that. No, not this. That's a textbook. Where's that slide deck? What do we got next? Oops. Yeah. Okay. Well, so this is now everything we've done so far has been related to concentration. But like I said, we could also do this for pressure, because pressure and concentration for gases at least, are related to each other. If the temperature is constant and it's a closed system, so gases aren't escaping, then we can say that Kp, or the equilibrium constant of the pressure, is equal to the respective pressures of the products risen to their coefficients over the respective pressures of the reactants raised to their coefficients. Okay. And yeah, let's go over a couple slides. We won't do any more problems, but I'll just put this here so that when we go over it on Thursday, it'll be a little bit, you'll have it lingering in your brain for a couple days. Okay. So you guys all remember PV equals nRT, the ideal gas law, right? If we get P by itself, then that is P equals N over V RT, essentially. We could write it like that. Now, if we take that equation, P equals NV over RT, and we apply it to our equilibrium expression for pressure, let's do this. No. Here we go. Okay. So we take this, we take our ideal gas law, and we take our equilibrium expression, and we just plug in what P equals, right? N over V times RT. We plug that in down here for P. We can write it as the concentration of C, right? Because that's the molarity, that's N over V, right? Moles over liters. Concentration of Z times the gas law of 0.08206 liters times atmospheres divided by moles times K, raised to the coefficient, blah, blah, blah. All right. Then we can further extrapolate out the gas law, or the gas law constants and the temperatures, and rearrange the coefficients so that we have them all on one side here. Now, coefficients divided by coefficients, right? X plus Y divided by something that's risen to the M plus N. If you guys remember, going back to that math in high school, is basically now we are subtracting them from each other. And so suffice it to say, we can take all of this stuff and squish it together and get Kc, right? Because what is this right here by itself that I'm circling right now? That's essentially Kc, right? The concentrations of the products risen to their coefficients over the reactants, that's Kc. So now we've plugged in Kc for this. Kc times gas law constant times temperature risen to X plus Y minus M plus N. Now what's X plus Y minus N plus N? That's just essentially delta N. What's delta N? Just a change in the molarity, or change in the moles, I should say. Okay. So we can say that Kp, the equilibrium constant of pressure, is equal to the equilibrium constant of the concentration times gas law times whatever temperature we are remaining constant, risen to the change in moles. Ah, what a way to end a lecture, huh? I don't care about you guys knowing how we got from here to here, okay? All this stuff is just, for those of you who are interested, showing you how we just don't skip steps, right? There is a logical way to get from one equation to another. Believe it or not, this isn't a math class, right? Math is just a tool that we use to understand how matter interacts with itself and with other matter. and how it changes. So I don't really care about you guys being able to derive these equations, okay? Just know this right here at the bottom, all right? Because when we continue on Thursday, we are going to do this kind of stuff. Come on. All right. We're going to solve for things. We're going to say that delta N is just the change in the moles. Okay. So down here, moles of product minus moles of reactant. How do you know what the moles of those are? The coefficients in the balanced formula. Okay. And so the problems will be simple. It'll give you either the KP or the KC. It'll ask you to solve for one of them. It'll tell you what the temperature is. You know what the ideal gas law is. If you have the formula, or if you're asked to derive the balanced formula, then you have the coefficients for the delta N, and you just solve for whatever they're asking for. Okay. And so next week, or not next week, Thursday, we'll do this problem where we're going to be looking for KC. They give us the KP. They must give us the temperature. Yes, 25C. Now remember, we got to convert that to Kelvin. And they give us the formula. So it's just basic algebra at that point. Okay, guys? Now, remember, journal club tomorrow for you section oneers. Journal club Thursday for you section twoers. Read the paper, write a critique and a summary, and turn it in before your group discussion. And also attend the group discussion. This is our last journal club this quarter. Okay? So let's go out with a bang. Read the paper to your best of your ability. And we'll discuss it, or you'll discuss it with Sean tomorrow. You got to be at the group discussion, though, to get the points, full points. Okay? Now, also, remember that your rough draft is due to Erina by the end of this week. Okay? Email her your rough draft so she can have a look at it and give you some feedback. Any questions?
We just have to email that to her by Friday. Is that right?
Yeah, email. I mean, ideally, email it to her yesterday, but yeah, just get it to her by Friday. That will give her some time to get it back to you, because the final draft is due next week, I think. Right? So you need to have time to see her comments if she has any. Oh, no, you got 2 weeks. You got 2 weeks. Okay. Sorry, didn't mean to startle you guys. 2 weeks before the final draft is due. Get it to her so she can get her comments on your draft and get it back to you. Okay. Cranium Cafe. Her email is on the homepage of Canvas. So if you go to the Canvas page.
It is also on Cranium Cafe.
Yeah, exactly. And if you guys want to, if you guys want to set up a time with her to meet live, she has her tutoring hours Tuesday and Thursday after lecture. Here, let me share.
And the rough draft is of the abstract and the poster, right?
Just the abstract, not the poster. Sorry, I don't think I made that clear necessarily, but just the written document. The poster, you'll just come up with that on your own. That said, if you want feedback on your poster, send it to each other, right? Get together and say, hey, how does this look? Any typos or anything does it look just graphically messy? Or, you guys are colleagues. I know it's hard to get together virtually. It's hard to know people, and when you don't see them, you sit next to them, and it really stinks, and it's awful. And I'm sorry. Prior to this, students had a much more mesh of a relationship, not mesh. And so it was easier to get feedback from each other. But here's Erin's email. Her tutoring hours 4 to 6, Tuesday and Thursdays. So if you just want to say, hey, Erina, can we meet so you can look at my abstract? And then she can go over it with you live. Or meet with her and say, hey, I don't understand what we went over in lecture today. You know, seek her out. But definitely email her that by the end of the week. Okay. All right. Well, you guys are free to go. Have a good evening. I'll see you guys, those of you who want to come to office hours tomorrow, Wednesday from noon to 1.
Bye bye.
Otherwise, I'll see you Thursday morning or Thursday afternoon. Okay. Oh, and Bennett wants, I don't know if you've seen this guy since he lost a tooth. Show him your mouth. Yeah, he's rocking the hillbilly look. Okay, so take care, guys. Have a good one.
Thanks,
Thank
Doc.
you.
Daddy, you know what's cool?
What?
This can come off and put back on. Look.
Oh, yeah? A detachable eraser. Yeah, that's neat. Okay, all done.
Brr. And now look. Oh, look at Lucas.
I like it.